Thank you for partaking part of our presentation. Our project is Implantable Medical Connectors. My name is Sam. We have Eric, Mary, Martha, and James. And our advisor is Dr. Kingsley Jones.
So there's an issue worldwide that affects people. People always get either neuromuscular diseases, they're affected by blindness, hearing loss, migraines. Oftentimes, to treat these diseases, people have surgery, painkillers, or injections, and this could affect people in their day-to-day lives. So another alternative to these kinds of therapies is a neurostimulator. And so what we're going to be doing is we're going to have a connector for the neurostimulator, because currently the neurostimulator is hardwired. And this basically means that the interchangeability between devices is much harder for the doctor and the patient. We're also going to minimize the size of the neurostimulator, and we're going to have a higher channel count in the connector in order to increase stimulation and to better treat other diseases like Alzheimer's. And we're going to make this connector out of biomedical material since it's an electrical component in a harsh environment.
Our design will consist of 32 pins, which will be on a connector the size of a 2mm by 6mm. Pins will be on one half of the connector, while vias on the other half, and they will connect by the pins going inside the vias. The pins will be an arrangement of a 3x10 matrix plus 2 on each end to make a count of 32 pins. And we will also be implementing an O-ring design for the hermetic seal, and as well as titanium clips to hold the two halves together. And as you can see in the image above, that is our preliminary testing that we've done in the Amory lab.
In the preliminary testing, as you saw on the previous slide, just to give the scope of the size that was placed on a dime on a microscope. And the way that we made that was we took sheets of LTCC, or low temperature co-fired ceramic material, which is pliable and we can handle it in the lab. Also alumina, which is HTCC, which sinters at a higher temperature than LTCC. And this is just for the prototyping stage to see if our design with the vias and the posts would actually work. So after the vias are punched, it's filled with a silver test material, which is conductive. And then after the layers are configured in the correct manner, they're stacked and laminated, after which will be, the assembly will be co-fired in the oven so that the low temperature material sinters, meaning it becomes harder, and the alumina will simply be brushed away. And the final design will be using alumina or the HTCC and platinum materials, as these are more biocompatible.
There's several tests that our device will have to undergo. The initial one is just conductivity to confirm that the electrical charge that's going in is coming out. Then we progress to the military standard 883 test, which is military standards for micro electronics. And that involves environmental test, electrical test, and mechanical test. And we specifically also need to incorporate test condition 1014. That tests our hermeticity, where it's exposed to a helium bomb. Since that's not naturally found in the environment, we then can test for any leaks. And then the next test would be the simulated body fluid test, where the device actually gets put in a saline solution at 37 degrees Celsius to kind of simulate the body to confirm for biocompatibility. Once these are all satisfactory, then it can go on to animal and human studies. The economic aspect are a sheet of LTCC is $20. We can get 25 squares out of this, which it takes 5 squares for one device. So we can get 4 devices out of this. I'm sorry, 5 devices. Bottle of platinum ink is $2,000 for 25 grams. The graphite ink is $700 for 100 grams, and silver is $125 per 100 grams. The platinum ink, the prototype, we're doing the graphite and silver to minimize cost, just to ensure manufacturability. And then the global component.
Being a medical device, we would want to be able to market to the entire global market. So we're going to be looking at FDA and EMA, which is the European Medicine Agency, to see if we can offer this in other countries other than America, Southern American countries and European countries as well. And just to give a scope of our materials are gathered from these sites, giving a more global aspect to the project.
And this is our plan for our project.
Question this one.
Pretty much self-explanatory.
Questions?
Okay, do you
Can you go back one? So you had a bunch of testing that you needed to be completed, correct? I don't see that anywhere on there. Oh, all the way to the
Last
bottom.
slide.
Oh,
Yeah,
sorry,
yeah,
I
last
can't
slide.
read it,
Yeah,
sorry. Sorry, I was looking for it. I saw final design before testing, so, okay, or anyway, it's fine. So, will you make any adjustments from that testing, or you're just gonna test this one specific prototype, and if that works, that's it?
Our initial testing is for the pen structure to make
Okay.
sure that it will sustain because it is such a such a small pen. So that's the biggest thing with design and modification is testing that pen to make sure that functions.
Okay, so what happens if it doesn't
If
function?
it doesn't function, then we have to redesign and look at other methods to manufacture.
Do you have any other ideas for that right now? I mean, you're just expecting it to work right now, or you have a pretty good, I'm just curious what your level
There are
of,
other possibilities as for mechanical connection. This is just to test the mechanical connection to
Right.
see if we can get
Well, sure.
connectivity. There are other ways using polymers, which you put the polymer on the entire structure, and once covering the certain paths that lead to the different connections. So once the polymer is under pressure, it creates a localized connection because it is a platinum polymer. The cells and the crystals localize in that area where there is a pressure, and in that area,
okay.
there's connection.
Gotcha.
So,
Sure.
and there are other mechanical.
Right, I'm just curious if there's a backup plan. So for instance, one of these tests go incorrectly. Typically with these ceramic vias, a lot of times any sort of stress on them, of course, it's ceramic, so you get breakage pretty easily, right? So if you do a hermeticity test and you guys can't maintain the proper pressure or anything like that, are you varying the thickness or are you varying the size of the vias or anything like that? But think about it. Anyway, can you go back to the testing really quick? So are you you're doing all of those tests, even animal and human studies?
We will not get to that point.
Okay, you might want to separate that out, just so that way, just looking at the slide, it looks like, hey, we're going to do human studies by putting in these things in people's brains. We're probably not going to do that.
No, we're not going to get to that point.
And for the simulated block body fluid test, what are you actually looking for in that case? Are you looking for cell culture?
Biocompatibility.
Well, no, but what does that mean? So what does biocompatibility mean to you?
To ensure that the,
No, I know what the word biocompatibility means, but what are you measuring?
Just to see if our materials resist the saline solution.
So you're just putting it in the solution and looking at it, or what is that test? What does that mean?
it has to sit in the fluid for a given period of time.
And then what?
Well, we also got to test the chromatic seal as well, the O-ring, see if any fluids penetrated the O-ring, and see, basically we got to take it apart and look at it under a microscope.
So you're solely going to leave it in a solution for a certain amount of time, then take it out and look at it?
Then there's an inspection, unfortunately.
Okay, all right, I'm just curious, I don't know what that means, that's all, I'm just trying to.
All I know is they're supposed to
Okay.
test for like corrosion on our product.
Okay, so what is the rate that you're looking for? Is there a specific?
We haven't got
Okay,
that
all
far.
right, just so that.
I have those answers ready.
Yeah, right, so try to, for your specific test plan, you should probably understand what you're looking for in each specific one. I'd also say you might not want to just put, this is just my personal preference, but just putting mill standard 883 and test condition 1014. If someone's looking up at the board and they're not paying attention, I know this is probably not their fault, not yours, but you might want just a little clarification of what mill standard 883 is and test condition 1014 is. Because if they look away for half a second or don't listen, they're not going to know what you guys
So
are
put a bullet point underneath. military
Exactly,
standards
just
for microelectronics.
exactly.
Or
Yeah.
parenthesis next to each.
Okay.
It's not a big deal, but it just helps with clarity throughout.
You want to make it clear.
All right.
Dr.
you're-
Basil?
Go-
Sorry, anyone else?
Yes, go back to your last slide, please.
Timeline?
Well, what's the slide after that?
That's it.
Don't even get me started, sir.
It should, the slide after that should be questions.
I know. What did I say to you today, Eric? Please take over the
We haven't spoken yet.
Have you finished manufacturing prototype?
Yes, the very initial one, but we haven't got a chance to test the pens yet to see if they're structurally sound.
So
So-
say you have finished, almost finished this. Manufacturing prototype, below that introduction. Yes,
Yes, December 14th, I believe it
yes,
says.
December 14th, it will be
It's
finished.
got 2 weeks still, I guess.
Yeah.
Yeah, so-
Have you done any testing at all yet?
No,
None whatsoever. So you're gonna start in December?
correct.
You need to change it.
Those
Say
are weeks.
November 11, right?
This is the
Testing.
weeks, so there's 4 weeks in September, 4 weeks in October.
And that bar chart for testing begins
Yes,
in
it
December?
begins.
Yeah, we got the product out, but we did not get a chance to test it.
Excuse me. You mentioned about the 32-pin microcontroller. Have you decided about that? Which model you're gonna use? The microcontroller? Yes.
There's no controller.
You're not gonna.
No, it's just a connector.
Okay.
Connecting the
It's just a
neurostimulator to the leads.
Also, it doesn't have that data analysis.
No.
Okay.
We come in maybe the same direction that Ben's comments. If you go back to the slide where you had that, and you say, I was going to add the same thing, you were going to work with animal and human studies because I have, I've been helping one senior design 2 this semester, and it's really the permits and all the stuff, it's really a huge problem. So you already gave the right answer. But going back where it says simulated body fluid test, maybe there my question was or is, how can you reproduce body fluid properties? For example, are you going to work with water or maybe with a substance
It's a
similar to
saline,
blood or?
no, it's a saline solution, and it's at 37 degrees Celsius. So, because it's not going in the blood system,
No.
it's outside. So the standard test for the simulated body fluid test is a saline solution, which is similar to a salt water.
So maybe there, just the same manner that you can clarify what test condition is, adding some information you can add in that point, maybe will you reproduce a body fluid with something different, okay? What properties are you looking for? Same density, same viscosity, same dynamic viscosity, things like this that will let the auditor know that you are taking care of those properties when you are going to simulate the bloody fluid test. Okay?
Okay.
Something like that.
Yes.
Any other questions? I think no, nothing.